Okay, so all right. So if you watched the previous video, then you know that here we're going to be talking about the singular value decomposition, and that is basically says that if you take a matrix A, we can decompose it into three different matrices: U, sigma, and V star. And where V and U are both unitary or orthogonal matrices. For here, I'm just going to talk about orthogonal matrices. So I'm assuming that A is going to be real, and then that's going to give us U and V real, and so I don't have to say V star. I can just say V transpose. And so rather than taking the conjugate transpose, I'm just going to take transpose. But otherwise, everything else works out just fine. So yeah, so this is all going to rely on the fact that you can find an eigendecomposition for a symmetric matrix, and then after that, everything else just falls out pretty quick. And then I'm going to give you a proof of the Eckard Young Theorem. This is straight from Wikipedia, and the singular value decomposition proof is coming from Gilbert Strang, but also interpreted through a blogger, Gregory Gunderson. Sorry if I botched your name. But yeah, they both, these are really concise proofs. It shouldn't take too long, and then after that we'll have the theoretical foundation to do everything else we want to do. Okay, so with that, I'm going to go ahead and jump into this. Okay. So let's go ahead and get started. This may or may not be my fourth or fifth take of this SVD construction, but you know, I swear I know what I'm doing. Okay, so let's go ahead and take a look. So we're going to start with a matrix A is a real valued matrix, or a matrix with real entries. You know, so it is an R m by n, so it has m rows and n columns, right? So n, right? Whatever that is. Okay, so basically, if you put a vector here, you can figure out exactly what size that vector has to be, because we need to have as many entries here as there are here, and so so A acts on say Rn and outputs Rm vectors, right? So, okay, so yeah, and basically the number of rows are determined by the rows of whatever is being multiplied on the left. Okay, so let's go ahead and take a look and see what we can do. All right, so first of all, we're going to say that A is rank R, and we're going to say that is less than n. Or less than or equal to n, and you can see that the rank of A is the same as the rank of A transpose A, and this comes from rank nullity theorem, which basically says that the rank plus the nullity has to be equal to the dimension of the domain. So how can we verify this? Well, we go the other way. We show that, so equivalently, we show that the nullity of A is equal to the nullity of A transpose A. And that basically means that AX equals 0 should imply that A transpose A times X should be equal to 0. Now, the forward direction of this is pretty simple, because if AX is equal to 0, then that means that A transpose times AX is going to be A transpose acting on 0, and so that's just 0, right? Piece cake. The other way just has to use a notion of norms. So if we take a look at X transpose times A transpose AX, and here we assume so we say if A transpose AX is equal to 0, then this is actually equal to, well, let's make it a little bit more explicit, AX transpose times AX, just because if you take the transpose out, then you need to exchange their order. Then this is the same as ax, the 2 norm for or the Euclidean norm for Rn squared, and so yeah. But we knew that on the other hand that this was equal to 0, so all this should multiply to 0. And so then we have the norm of ax is equal to 0, which then implies that ax must be equal to 0, because the only thing that has norm 0 is 0. Okay, so so there we go. We know that the rank of A transpose A should be the same as the rank of A. Now let's go ahead and figure out what needs to be in our domain. So we want to figure out, we want to break up our domain into orthogonal pieces. And so what we do then is we take a look at A transpose A, and this is positive semi-definite and symmetric. Sometimes symmetric is included in the definition of positive semi-definite. And so how do we know that this is positive semi-definite? Well, we already basically showed this. If we take x transpose times A transpose AX, this is equal to the norm of AX squared, and this is always bigger than or equal to 0. And this is the definition of positive semi-definiteness. So yeah, so that works just fine. Then what does that tell us? It says that A transpose A has an eigendecomposition. Right? So that means that A transpose A is equal to, say, some V times lambda times V transpose, where lambda is diagonal, composed of eigenvalues for A transpose A, and V is an orthogonal matrix. Another way to rewrite this is that we could say that this is the sum I going from 1 to n of say lambda sub I times vi times vi transpose, and so this is a rank 1 matrix, or rank 1 tensor if you prefer. Okay, and so this is the standard decomposition, eigendecomposition of matrix. But something that we can take away here is that this can also be written as a sum I equals 1 to n of sigma I squared of vi times vi transpose. What is sigma I? These are the singular vectors, singular values. And yeah. I'm just declaring them, defining them as, say, sigma I is defined to be the positive square root of lambda I. So that's where you get your singular values from. Okay, so now we are guaranteed that A transpose A is diagonalizable because it is a positive semi-definite matrix, so that means that these VIs span the space, and so we have our domain. Decomposition is this basis v1 up to vn, and these are all vectors in Rn. Okay, so we can take any vector in Rn and decompose it in terms of v1 through vn. Now we want to be able to decompose the range space, and so please excuse my my notifications there. How do we get UI? So what do we do about the range? Well, turns out we can also get a decomposition for the range, and so this is we're going to define A times VI divided by sigma I, and we're going to call this UI. It turns out these are orthogonal. It's pretty cool. You can basically say UI transpose times UJ, and this is going to be A VI over sigma I transpose times A VJ divided by sigma J, and then using our operations, we get 1 over sigma I sigma j, and then we get vi times A transpose A times Vj. But we just declared that Vj is the eigen vector for A transpose A with eigenvalue sigma j, and so this gives us sigma j divided by sigma I sigma j, just leaving that in here for clarity, times Vi transpose times Vj. Since we know that the V's form an orthonormal basis, if I is equal to j, then oh, sorry, that should be squared here. Good thing I left it there for clarity. So if I is equal to j, it goes to 0 because these are orthogonal. And if they're not, if I is not equal to j rather, and I is equal to j, it goes to 1 because sigma j would be the same as sigma I, and so it would be squared on top and bottom. And then since they're and then Vi inner product with Vi is just 1 because they're normal vectors. Okay, so I should also declare this is an orthonormal basis. Okay, so now let's see what we get. So what I basically just told you is this. Okay, so let's see what we've talked about so far. So basically, I'm saying that if you take A, you multiply it times V, that's going to give you U times sigma. What is sigma? Sigma is sigma 1, sigma 2, all the way down to sigma n and 0, and that's our singular matrix. And so it's diagonal on the upper piece, and then there's like a 0 chunk on the bottom, which is just has no content. This V is going to be the matrix that's composed of V1 all the way down to Vn, and this U is going to be the matrix that's U1 up to Un, where they're all defined by this. Okay, now how do I get to A? Well, since V is an orthonormal basis, if I multiply both sides by V transpose, then over here it'll just cancel it out, and so we're left with A is equal to U sigma times V transpose, and there you go. That is your singular value decomposition. So yeah, so that's that. And now let's go ahead and talk about the next thing, and that is the low rank approximations and the best possible one coming from the SVD, and this is called the Eckard Young Theorem, or Eckard Young Theorem. Minsky theorem? I can't pronounce this. Okay. All right, so today here I'm going to end up talking about the Eckard Young Minsky theorem, or just the Eckard Young Theorem, and this was out of 1936 in psychometric. I think I mentioned it before in the last video. Anyway, so basically what we're going to say is we're going to take a matrix A, which is m by n, and oops, not raise the m by n. A is a real valued matrix of real entries, where it's an m by n matrix. And we're going to write it as A is equal to U sigma V transpose, and this is our singular value decomposition. And our claim is that if I truncate the singular value decomposition, that is the best possible it's the best possible approximation A of rank K where we truncate it. So claim the rank K matrix given by A, we'll put sub K is equal to sum I equals 1 to K of sigma I times Ui Vi transpose. Okay, so the rank K matrix given by this is the best approximation of A by a rank K matrix according to we'll say the spectral norm. This also holds for the Frobenius norm, and you can see the proof on Wikipedia. I'm honestly following the proof from Wikipedia, but I'm going to try to fill in extra gaps in here too. So, so what is a spectral norm? This is one gap that I should mention. So a spectral norm. All right, so this is a norm that is determined by the eigenvalues. So for a matrix A, the spectral norm denoted by, or denoted as, the norm of A sub 2 is the largest singular vector of A. Rather, it is the largest eigenvalue of A transpose A. Okay, now the first thing I want to show you is that if say, we'll say this, if W is in Rn, not A, right, Rn, with a norm of W2 being 1. Now this is Euclidean norm, vector. We're not talking about the two. Actually, that might work as the 2 norm for that too, but let's not get confused. This is just the regular Pythagorean Euclidean norm here. So if that happens, if this is just 1, then the spectral norm of A is going to be bigger than or equal to A times X, or A times W 2. So this is an Rm vector, and this is a spectral norm, right? And that's easy enough to prove. So basically what we're going to have is that, so what we're going to basically show is this. So we can say A times W 2, and let's say that's squared. Now that's the same as AW dot product with itself, and so this could be written as AW transpose times AW, and this is the same as W transpose times A transpose AW, right? Now I can put this in absolute value. It's just real number, and it's a positive real number, in fact. And what I can get then is I can use Cauchy-Schwarz, and I can say this is less than the norm of W2, say squared, times A transpose A times W squared. Since A transpose A is diagonalizable, that basically means that I can break A transpose A into an eigendecomposition, and that means that W could be written as an eigendecomposition. So W could be written as, say, K1 V1 all the way up to Kn Vn, keeping the same eigendecomposition we had for the SVD, and so then this is equal to W2 squared times the square root of K1 squared up to times sigma 1 squared all the way up to K1 sigma Kn sigma n squared. Boop. And I should mention, I didn't think I mentioned it before, I probably should say it here, we write this in decreasing order. So we say sigma 1 is bigger than sigma 2, bigger than all the way down to sigma n, right? So all right, so we do that, and so basically we know that these K1s in norm have to add up to 1 because W is of norm 1, and by the way, since W is of norm 1, that means that this is 1 as well. And so this is basically a weighted average of things that are less than or equal to sigma 1 squared. And so this, and this should also have a square on it, that should have a square on it, sorry. And so then we end up getting basically sigma 1, this is less than or equal to sigma 1 squared, and that is by definition the spectral norm of A. Whew, okay, all right, so now equipped with this, we can actually go and actually look at the proof itself. So, now, remember, we're dealing with, let me just go right, A sub k, which is equal to sum I equals 1 to k of sigma I times ui vi transpose. And basically what we have is we have A minus ak, and that, since A can be written basically like this, but with an n up here, this is a sum I equals k plus 1 up to n of sigma I ui vi transpose. Okay, but just like what we talked about before, the largest singular value here is going to be sigma sub k plus 1. Okay, so now what we need to show is that if B is a rank k matrix of the right dimension, such that we can write B, and let's say B sub k is equal to x times y transpose, then we want this. We want to show that A minus BK has to be bigger than sigma k plus 1, or at least bigger than or equal to. All right, so which would then make the approximation worse than if we just use this. All right, so that's not too bad. Basically, since y has k columns, or rather we can write any rank k matrix as a product of two matrices, each with k columns. So x and y have k columns. Right. So since y has k columns, that means that if we take the first k plus 1 VIs, then there exists some weights. There exists a W that could be written like this, gamma 1 V1 up to gamma k plus 1 vk plus 1, that is in the null space of y. And this just again comes from rank nullity theorem. The rank of y is going to be k, and so that basically means that if we take a look at the span of the VIs, which are dimension k plus 1, there has to be at least one direction that we can go in that's going to be in the null space of y. All right, so again, this is rank nullity theorem. Okay, and so I'm going to also assume that W is of norm 1, just like we talked about before. Okay, so what does that give me then? Well, I know that the spectral norm A minus BK and 2 has to be bigger than or equal to A minus BK applied to any unit vector, right? And that's what we just proved a minute ago. We're going to square all these guys for good measure. And since W annihilates Y and BK is, should be a null space of Y transpose. There we go. So that way, when I put W here, this guy ends up being 0, and then the whole thing 0, right? So that's what we need, Y transpose. So then we know BK hitting on W is just going to be 0, and so this is actually exactly equal to A times W, 2 squared. And then we know since A can be written in terms of this, so it's basically going to be, we're looking at the sum of sigma I ui vi transpose acting on W, which is gamma 1 v1 up to gamma k plus 1 vk plus 1, and so and this squared. So this is I equals k plus 1 to, no, this is just A. So this is 1 to n. So basically you can use the fact that vi transpose attacking, say, v1 is going to be 0 unless I is equal to 1, and etc., etc., and so using the orthonormal property. And so ultimately what this ends up giving you is this. It gives you the sum I equals 1 to n of sigma I times gamma I times ui. And then what is known with this? Well, ui is also an orthonormal basis, so that basically means that this has to be equal to the sum of sigma I squared times gamma I squared. I equals 1 to n. And actually, it shouldn't even be up to n. We can stop at k plus 1, because otherwise everything's 0, right? Because we just stopped here. And yeah, we know that this, again, since the sum of these guys is going to be 1, this is a weighted average of these sigma i's, and so this is going to be, all these sigma i's are going to be bigger than or equal to sigma of k plus 1 squared. Because all the previous ones are bigger than it. So there you go. Then you just take square root of this side, and we win. And so there we go. There's the Eckard Young Theorem for the spectral norm. Okay, so I think this is probably a good place to stop, and that gets you sort of the beginnings of the theory that comes with the SVD. Some things I should also mention here is if we go back to here. So here we have that u up to 1 through n is going to be less than the dimensionality of the range space. So what we do typically is we pad on extra u's that come from the perp space of the span of u1 through un. And then that'll make that a square matrix, and that makes the sigma have some 0 padding at the bottom. And you end up having the domain dimensionality being larger than the range dimensionality. You can still do an SVD on A. You just take A transpose, do the SVD, and then transpose it back at the end of the day, and then that will take care of everything. All right, so I'm going to stop, and that's a lot of jabbering and blabbing, and hopefully it's somewhat coherent, and yeah, I'll jump back to my office. Okay, so those are the two proofs. Basic linear algebra, nothing really too fancy. So this gives us a nice, very simple introduction to this class. So the SVD is going to be very important, and I'll give you a few examples that are used in dynamical systems, but also some that aren't, just to give you an idea of how it's used, and we can even talk about some very relevant things that we can use the SVD for right now. So with that, I'm going to stop, and yeah, I'll see you next time.